In this video, I'll discuss how the work done on an object may or may not depend upon the path that the object takes as it moves. So if a conservative force does the work will be independent of the path. So let's look at that first example. I have two diagrams here, and this is a slope, kind of like a ski slope perhaps, and an object sliding down that ski slope. Here, the object goes from this position A, to position B. It travels a height of h. And the slope, it travels a distance we'll call d1. Now, right next to it, we have the same height, but this hill right here is not as steep. So that means that d2 is greater than d1. So that's the difference between the two. This is steep, and this is less steep. So in this case, we can summarize what happens with the energy exchange. We know that all the energy at position A has to be equal to all the energy at position B. So the total energy at A equals the total energy at B. That's true for the steep hill, and that's also true for the less steep hill. So the only energy that you have at position A would be mgh, the gravitational potential energy, and the only energy you would have at position B would be the kinetic energy, 1/2 mv squared. So you see that mass cancels, and you can rearrange the formula to read that the velocity at the base of the hill only depends upon how high the hill is. The same is true for the less steep hill. You see that the d, the distance, the length of the hill, and the angle of the hill is not important in the calculation. That will be true if you're using conservative forces. However, what if non-conservative forces such as friction is present? So as the object slides down the hill, it encounters friction also. Well, in that case, the scenario is much different, because what we have is initially we have the total mechanical energy. That would be the gravitational potential energy and the kinetic energy, plus the work done by non-conservative forces. Work done by non-conservative forces are in the negative direction, so this will be negative value. And these two values have to add up to the final energy. So let's expand this. So this would be the case for non-conservative forces. So at the top of the hill, in both cases, we start off with mgh. That's the source of the energy, the gravitational potential energy. As the object slides down the hill, both hills, it encounters friction. So that would be minus ff times the length of the hill that it encounters. And that's going to be equal to the kinetic energy at the bottom of the hill. So if we have friction, you can see that the final velocity will depend upon that friction. And friction depends on how long, or the work done by friction depends on how long the hill is. And the length of the hill depends on the angle. So let's analyze this further. So mgh remains. We expand ff. Ff is mu n times d. And that's equal to the kinetic energy at the base of the hill. Further expanding, we still have mgh. Now we have mu mg cosine theta times d. N, the free body diagram, I didn't draw that here. You can draw that yourself if you need to. The normal force acting on that object is equal to mg cosine theta, similar to all of the inclined plane problems that we've done previously in the course. So you can review those notes if necessary. So again, mgh minus the work done by friction is equal to the kinetic energy at the base of the hill. If we rearrange this, we see that the velocity is dependent upon the distance, which I failed to add here. So I'll just squeeze that in. My emergency red pen. There you go, that's better. So we see that the velocity with conservative forces is only equal to the square root of 2gh, But if there is non-conservative forces such as friction, the velocity is equal to the square root of 2gh minus 2 times the work done by friction. So if a non-conservative force, example, friction, is present, the work done on an object depends on the path that it takes. It depends on d. If a non-conservative force is present, the larger the d, the greater the work done by that non-conservative force. So in the case of our slopes, the longer the slope, the more joules are stolen from the problem by the work done by friction. And the consequence of that is the longer the slope with friction, the slower the object will be after it reaches the base of that hill. So finally, if only conservative forces are present, the non-conservative work is equal to 0, so work is independent of the path.